Again, hi and welcome to today is actually April 26. We have quite a bit of material to cover from this class. We still have chapters 28, 29, 30, 31, and 32. So we have a lot of materials to cover. So, and also in terms of applications for chapter 27, I'm going to combine them with chapter 28. So we're going to jump into chapter 28 today. And hopefully we will cover it, and then we're going to come into chapter. We're going to come to chapter 27 and 28, basically in it. Okay, let me share with you the screen. Share, so that we see what we're doing. Okay, so the idea is what we covered before, basically from chapter 27, and that is really the main thing that we have in that. So it's the magnetic field. The B in here stands for the magnetic field of the magnetic force in this case of a charge moving inside the magnetic field is given by this expression. That is really the point in here, as opposed to the electrostatic force that was given by this expression, Q times E, that's all. Okay, the combination of the two is the force, the Lorentz force, which is basically how much a magnetic field and electric field influence a point charge, Q. And we also derive an expression for the force, basically for a wire, and a wire that has a current I running through it. And if I take an element in here, L or dL, okay, we saw that it's going to basically be subject to a force in this case inside the magnetic field, and that force is again equals to I dl crossed with B, and this is basically the force on a wire, okay, by magnetic field. So this is in a nutshell what we have seen last time, okay. In general, it's this is dF, okay. So this is a force on this element only, not on the entire wire. So this is basically in a nutshell what chapter 27 was, and that is what the effects of the magnetic field on point charges and wires. So those are the two things. Effects of a B field on a moving point charge and conducting wire. A wire are carrying current I. So that is basically in a nutshell what we have seen from the previous chapter. And again, like I promised, we're going to come back to it for more applications. Chapter 29. Chapter 29 deals with another thing, and that is what causes magnetism. That is really an important point. We really need to know how can we create a magnetic field. For that, we're going to rely on an experiments, and the experiments basically can be summarized by the work of Biot and Sabart's law. Before that, a point charge can create, again, a moving point charge creates a magnetic field. So this is an experimental law, just like Coulomb's law. Remember when we did the electrostatics, we said that a charge will create basically a force, and then we can work out the details of that force and basically get rid of the charge. And at the end, we have an electric field. So for a point charge, you have an electric field that was given 1 over 4 pi epsilon naught times the charge divided by r squared times r hat. Okay, where r hat points from the point where the charge is to where we want to find the electric field. So imagine that there is a point charge in here sitting in space. It doesn't have to be moving. And then you want to find the electric field in this point. So this is the distance r, and this is r hat, the unit vector. Okay, So the electrostatic field then here is given that way, assuming that Q is positive. If Q is negative, the electric field points in the opposite direction. That's all, because the sign of Q will take care of that. So that's the electrostatic field. Now, for the magnetic field, it's similar to that, except the expression is a little bit different. So it's B, first of all, is equal to a constant, which is called the permeability of the medium. And we're going to talk about exactly what that is, times the charge, times the velocity of the moving charge, times the unit vector r hat divided by r squared. Let me represent it again. So we have a charge now in motion. So it has a vector v already. So this is q, and that is what the direction of v is. And I go to a space in here, in a point p in space that is situated at a distance r from the charge. So there is an r vector, and this is your r hat. Okay. So this is the point where you want to find the electric field. From here, you can tell that the magnetic field now that is created by this charge is not in the direction of r hat, but rather is in a direction perpendicular to r hat. And it's also in a direction perpendicular to v. So I need to form this cross product, basically. I can translate this vector in here. This is v. And I need to form this cross product. Cross product in this case is v crossed with r hat. So it's going to be a vector that is going to be pointing inward, actually. As a matter of fact, this is how the direction of the magnetic field would look like. It's going to be here, picture, okay? Because you have v crossed with r hat, and the picture now is going to go into the screen. So that's where the direction of the B field is. So it's not, this is completely different than this picture. In here, because you didn't have a cross product, the direction of the electric field and the direction of the r hat are in the same direction. In other words, E is in the same direction as r hat. In here, B is perpendicular to r hat, and also it's perpendicular to V too. And it's perpendicular to the plane they form. Okay. The magnitude of this vector, if you're trying to find B in magnitude, it's mu naught divided by 4 pi, 4 pi only, times the Q times V times R times sine of this angle, whatever that angle is, let's call it theta, times sine of theta divided by R squared. As this particle is moving, it's creating at that instant that magnetic field. So if it keeps that direction, then of course the theta doesn't change. But if it starts to move one way or the other, theta changes. And in doing so, actually, R also changes. There is no R in here, I'm sorry. It's already the unit vector. So there's this is the unit vector. So its magnitude is already 1. Okay. So it's QV sine theta divided by R squared. Okay. So that is the strength of the magnetic field. Again, this is an experiment. So this thing in here is really different, big time, than the electric field in terms of direction, in terms of this cross product that really messes up things big time. Okay. Okay. So in here, the direction is given by the right-hand rule again. So this expression is a little bit more complicated than this one for the magnetic field than the electric field. Let's take a wire now that has a current. Again, this is experiment. This is not a theory or anything like that. So if I have a wire in here, and if I focus on this element of the wire, so I'm going to take that element of the wire, I'm going to blow it this way. So it's still that element that I'm looking at. I'm not just taking the entire wire. So this element has a length DL. Obviously, it's part of a big wire that has a current running through it, I. So there is a current in here, I. And the direction of the DL is in the same direction as the current. So if I choose this one, DL, this vector DL points in the same direction as the current, okay? And if I'm interested in finding the magnetic field, let's say, for example, at some point in space here, okay? The experiment has shown that, of course, the element DL is so tiny, okay? So you're asking, where is this starting point? Is it in the middle? Is it on this side? Is it on this side? It doesn't matter. It's so small that the starting point can be anywhere. It's just a point in space, okay? So the experiment again, this vector is R. This is your R hat, okay? And this is the current in here. The experiment has shown that the element, the magnetic field created by this element. The reason why I'm using the differential form D in here, because I know this is not the entire magnetic field due to the entire wire. It's just a small element of it. And that is given by mu naught over 4 pi times I times dl crossed with r hat divided by r squared. Okay. It's still similar to that of a point charge, except now instead of talking about the current, which is Q times by unit time, here if I divide Q divided by delta T, that would be the current, times delta X in here. So in other words, this V, I can write it in here for that element as delta X over delta T, and divide Q by that, that is my current, and then here I have delta X. In terms of units, it's the same thing. Everything matches in terms of everything. Except now I'm taking an element of a wire. So this current I is throughout the entire wire, and I'm taking an element of it dl. So this law has a name first of all, and I'm going to talk about that mu naught because it happens in here several times. This law is due to Biot and Savart law. That is what it's called. Similar, if you wish, to Coulomb's law. Not the same, similar. In terms of role, this one gives you E, this one gives you B, okay? Let's talk about mu naught. In the first law for Coulomb's, epsilon naught was downstairs, was in the denominator. This is actually upstairs in the numerator, okay? So this is a big distinction that we used to see everywhere we had Coulomb's law, everywhere we were dealing with the electric field. The permittivity of the medium, which is epsilon naught, was in the denominator. The only exception was when we were dealing with the energy density. The energy density, if you guys remember, for the electric field was 1/2 of epsilon naught times E squared. So that is the only exception to the rule where epsilon naught moved upstairs, moved to the numerator. Mu naught now appeared from the get-go in the numerator, okay? So that is a big distinction. So mu naught is the permeability of the medium, not mu naught is the permeability. We're still in not doing any theory at all. This is just experiment, okay, of the medium. You can take 4 pi, I'm sorry, mu naught is equal to 4 pi times 10 to the negative 7. Let's talk about the units now. The magnetic field is in Tesla. And this has the units for mu naught times the unit for the current is in ampere. The unit for the distance, dl, is in meter divided by meter squared. And that cancels this one. I'm left with the meter downstairs. So the units for mu naught are meter times Tesla divided by an ampere. So it's Tesla meter divided by an amp. So this is the value that you're going to be using in here, okay? Remember, and this was actually, it annoyed me so much, and I hope that I should have made a note of it during the exam, that some of you were, instead of multiplying, they were dividing. So 1 over epsilon naught, okay, 1 over epsilon naught is actually equal to, what is it, 4 pi times 9 times 10 to the power 9. And again, you can find its SI units by going back to the definition of how we found it, okay? See how much the difference between them? And both of them appear in this fashion. Let's be clear on that. Everywhere we were dealing with the electric field, we had 1 over epsilon naught, and 1 over epsilon naught is a huge number. Epsilon naught is a tiny number, but you divide by a tiny number, you end up with a huge number, okay? So the electric field now, from in terms of order of magnitude, already have 1 over epsilon in it. So whatever you have in here, it's enhanced by that 1 over epsilon naught, which is 9 times 10 to the power 9 with this 4 pi. This guy, on the other hand, is multiplied by mu naught, and mu naught is actually a tiny number. So the magnetic field is actually appears to be of a lower intensity when it comes to values, at least compared to the electric field. So that is one note in terms of, so this is the permittivity actually. Epsilon naught is the permittivity. And why not? And mu naught is actually the permeability. Just when we did the dielectrics, we found that the dielectrics have a relative epsilon r that is not necessarily equal to 1, and it's equal to 1 only for vacuum and air. Okay, the same thing in here. There is a relative permeability for magnetic materials, and they have a mu r. Okay, and it's only equal to 1 for air and vacuum. Okay, otherwise, for a material that has magnetic properties, mu r can be actually different than 1. Okay, more than 1. So that is really the connection between the two. Okay, so that is where we are right now. Okay, in terms of constants, at least in terms of units and everything else. Now, word of caution, this expression is bad. Let me rewrite it again. Okay, so I have an element of current, and this is an empirical law, so don't ask me to prove these things. This is based on observation, based on experiments. A lot of people worked on this. So it's I times dl crossed with r hat, I'm sorry, unit vector, divided by r squared. Okay, this expression has the 1 over r squared. Okay, which created a lot of problems for us when we were doing electrostatics. When we're doing now magnetostatics, these v's have to be constants. The current has to be constant. Okay, so we're dealing with a situation where I is constant. Okay, it's not changing the time. If it is, then we have another problem before us. There is no time dependency. So this is magnetostatics. Okay. The point in here is this expression involves a cross product. Okay. And because of that, cross product expression is not really easy to calculate. It's not easy to imagine. It requires more work from you. Okay. So the first thing we're going to do with it is we're going to apply it for an infinite wire to see how much magnetic field is going to create for us. So that is basically the challenge right now. So we want to see how we can find the magnetic field of an infinite wire. Magnetic field created by a long wire. So what we have in here, we have a wire that is super long, and we want to go distance, I'm going to call it r, from the wire, and I want to find the magnetic field in that point. I'm going to take the direction of the current to be in this direction. So this is I, okay? So I'm going to take, actually, as a matter of fact, the origin of this wire in here. This would be negative infinity, this would be positive infinity, and this is a point x in space, okay? Going to go distance x plus delta x plus dx, and consider that my wire, okay? My finite element of wire dx. So obviously this wire in here has a length dl equals to dx, okay? And you can clearly see that dl from this picture is in the x direction, okay? So if that's the case, obviously this dx is exaggerated in here to being too large, but I'm going to take this. This is the direction r. I use the symbol r in there. So let me use this one in here as being the distance y, okay? So that this is distance is y. So this r is clearly equal to square root of x squared plus y squared. Does everybody agree that in this representation? Because this distance is x from the origin, and this distance I just changed it y. The reason why I want it to y is because in the formula in here for Buterin-Savart's law, we have an r in there. Make sense? Okay, very good. So the r hat in here is clearly, this is the vector r hat we're talking about. Okay? Because we take it from the element, dl, and we go straight to the point where we want to find the magnetic field. So that is the whole point in here. We want to find the magnetic field in that direction. Okay? So you can clearly see, and I'm going to make the case for it. This is I hat. This is R hat. R hat has two components. Okay, the unit vector has, if I'm going to call this angle theta. And let me remove this y from here, okay, because it's in the way of things right now. So this angle is theta, and this is y. This distance is y, okay? First of all, tangent theta, you guys can clearly see that tangent theta is x over y. Opposite over adjacent. That's tangent theta, okay? The direction in here, it's in the negative direction in the I hat direction. So this is your vector I hat, by the way. And this is your vector j hat, okay? The vector r hat is positive in the y direction and negative in the j hat direction, in the I hat direction, okay? So I need to find its direction because I took the points in the positive direction. Had I taken it in this direction, then it would have been different, okay? Then it would have been both of them in the positive direction. If I took the point x in here, then this will be r hat, okay? And then that would be a different story there, okay? But then x would be negative. I'm taking x positive in here. So r hat, I'm going to write its expression and tell me if it's wrong. It's simply, you can clearly see, it's r hat is simply r over r. R hat is simply r over r. Because it's the unit direction in the vector in the direction r. So r itself as a vector is its length times r hat. That's all, okay? And what is the length of this vector in terms of its components? The x component of this vector in the x direction is minus r, and I have to take a direction minus r because r is pointing in this direction, okay? Times the opposite to theta, and that is sine theta in the I hat direction. And then the y hat direction, which is positive, r times cosine theta in the j hat direction. Do I have it correct? Do I have my angles correct? Looks like it. Yeah, it involves the sine of the angle between them. Yeah, it looks like right, okay? Because the x direction in here, it's this whole thing. And this one is the opposite to theta. So it's sine theta. And this one is the adjacent to theta, and that is going to be correct. So in other words, x, you can clearly see, in magnitude only, it's equal to r sine theta, and y in magnitude only is equal to r cosine theta. And that's why x over y is tangent of theta. But then that's a magnitude, but the direction of r is opposite in the x direction. It's pointing in the opposite direction. So again, I'm going to just continue with this thing in here, and we should be able to get an expression for everything after we're done with it. Let's let's see in here if we get to the correct answer or not. Okay, because I have a feeling that there is something wrong I'm doing in the calculation in here. But hopefully you guys can correct this one. So that was Rx. This is Ry, the component in the y direction of the vector R. Okay, so again, when you divide by R hat by R, so the R cancels and the vector R hat itself will simply be equal to the vector whose components are minus sine theta and cosine theta. Okay, in other words, it's minus sine theta I hat plus cosine theta j hat. Okay. Okay, so now we're going to come in here to this expression now and do that dot product, do that cross product, I'm sorry. So the dB for the element itself is going to be mu naught over 4 pi times dl times the current, first of all, I, times dl. And dl is dx in the I hat direction, crossed with, oh yeah, that's correct. Everything is good. Crossed with this vector R hat. And the vector R hat is minus sine theta I hat plus cosine theta j hat. Okay? Divided by R squared. And R squared is just the square of this number, that's all, which is x squared plus y squared, which is x squared plus y squared. Okay. Now, properties of the cross product. I hat crossed I hat, that is 0. Because when you cross a vector with itself, basically you're going to end up with the length of the first one times the length of the second one times sine of the angle between them. So it's going to be I in length, which is 1 times the sine of the angle between them, and the sine of the angle between them is sine of 0. So that is why the cross product of any vector with itself is 0. So if you cross any vector A with the same vector A, you're going to always get 0 no matter what, because the sine of any angle, sine of any vector with itself is going to be 0. So that is not going to be a problem. It's I hat crossed with j hat, that should be k hat. Okay, and you can do the stuff from here. Again, if you didn't do this before in the past, this is just a quick in here refresher. So this vector can be found with the determinant method. So again, I hat, the first vector has 1, 0, 0. The second vector is 0, 1, 0. And this one, if you do the product for I hat, it's going to be 0 squared minus 0 times 1, which is going to be 0. So it's going to be 0 I hat plus the j hat in here, which is again 1 times 0, which is 0. Plus 0 or minus 0 squared, that's going to be 0 j hat. And then at the end, you will be left with 1 times 1 minus 0 squared. So it's going to be k hat. So again, that is part of the properties of actually the cross product for the Cartesian coordinate system, is that always I cross I is 0, or any similar vectors are 0. And I cross j is k. And then this is a cyclic operation, actually. Okay. And there is a symbol for it that is used similar to the chronicle symbol for the cross product. Anyway, we're not going to get into that. So this is going to give you 0 because they're in the same direction. And this is going to give you k hat. That's all. Okay. So the magnetic field is in the k hat direction. So assuming that this is the x direction, the other one is the y direction, k hat is coming out of the screen. So this is where the magnetic field is actually pointing. It's coming out. So this is your dB. Okay, so it's coming out of the screen in this point. If we did it in the bottom, if we did it here, actually, we're trying to find it, it should be going into the screen because everything is the same with the exception now, this component will be in the negative direction. So you will have a negative in here. And that negative times k hat will be negative k hat, so it will be pointing into the screen. So the magnetic field seems to be actually will be curling. So if I take this whole wire and look at it from the other side, this is how it looks like, the wire. It's coming to me. So I'm going to go in front of the wire. So this is the first time we're looking at it this way. But if I flip it and look at it this way, So basically you will see a point in here, and it's a point coming to you. Otherwise, this is how it looks like. So that is how this is. So if I go from one end and look at it from here, where the wire is coming, the magnetic field in this point is pointing this way, actually. It's perpendicular because now it's coming out of the screen in this picture, but in the other one, it's going to be actually perpendicular to it, and in the bottom, it's going to be this way. As a matter of fact, if I draw it everywhere, it's going to be on a big circle in here, okay, in this fashion, okay? So it's curling. So this is the direction of the current with a right-hand rule, of course. The magnetic field will curl around the wire in every direction in here. And like the electric field, as a comparison, which was like a hedgehog in here, coming out in all directions, if we were calculating, if it was a point charges, if it was distribution of a charge, this is how the electric field would look like in here. Perpendicular. However, the magnetic field is going around in a circle, okay? A distance y from the circle. I'm assuming that this distance is the same distance y. So that is one property, and it's coming from this direction, from the cross product, okay? So let's plug in the stuff and see how much numerical value is going to be. So again, dB now, this is not the full magnetic field. This is just a magnetic field due to just an element of the wire, dx, okay? So we need to sum through that dx from negative infinity to positive infinity to find the whole contribution. So again, it's minus, I'm sorry, what do you mean minus? It's mu naught I over 4 pi times dx. I'm going to leave dx for right now. Times, I still have a cosine theta in here coming from this cross product. That's a constant. I mean, as far as the vectors, it's no direction. And the vector is pointing in the k-hat direction, divided by this distance squared. This distance squared is x squared plus y squared. Y is constant, by the way. So it's y squared plus x squared. X is the one that is changing from negative infinity to positive infinity. So we need to really sum from x, negative infinity to positive infinity to find all the contributions for the entire wire. We need to do an integration in here from negative infinity to positive infinity of this expression. We have a handy transformation in here from this ratio of y, x over y, that is tangent of this angle. So instead of doing the summation through x, we're going to do the summation through through theta, I'm sorry. And theta changes from this angle, which is negative pi over 2, because when negative infinity, this will be parallel, and this angle will be negative pi over 2 to positive pi over 2. In other words, what is the arctangent of negative infinity? That is negative pi over 2, that's all, okay? What is the arctangent of positive infinity? That is pi over 2. Again, that is coming from the properties of the tangent. Tangent has this property. Tangent of 90 degrees is infinity. Tangent of negative 90 degrees is actually negative infinity, because again, it's a sine theta over cosine theta. Sine of 90 degrees is 1, cosine of 90 degrees is 0. That's why you're dividing by 0. That's why the tangent is infinity. So the boundaries of integration will change. Instead of x going from 0 to from negative infinity to positive infinity, to simply theta going from negative pi over 2 to positive pi over 2. That's all, okay? And everything else should be the same if we express everything in terms of theta now instead. So B now, before we do that, let's continue with dB a little bit, expressed in terms of theta though. So I have to do the dx first, okay? Because we have a dx in the denominator, if you guys see it. If we don't do that, we have a problem. We have the dx. We need to find dx. Remember, the expression that we ended up with is tangent of theta. This is a change of variable that we're going to take, is x over y. And y is constant, by the way. So x is equal to y times tangent of theta. So all I have to do is take the dx by taking the derivative of this theta with this tangent with respect to theta, and that is the secant squared. So it's going to be y times the secant squared of theta times d theta. Does everybody remember this expression in here from your calc classes? The derivative of the tangent is the secant squared. Okay, very good. So we're going to plug this expression in here for dx. We're going to pull an y squared in here out of the denominator to get rid of this x, or just sub the value of x, which is y tangent theta. So it's going to be y squared plus tangent theta squared. So the dB now is going to look like dB is going to, first of all, I have a mu naught I over 4 pi times dx. dx is y cos squared of theta, not cos squared, secant squared, I'm sorry. It's y secant squared of theta d theta. That is my dx times cosine theta. I have a cosine theta in here. Cosine theta k hat divided by x squared plus y squared. It's y squared plus y squared tan squared of theta. Okay. So I'm going to cancel one of this y squared with this y, and I'm going to pull the y to the other side. So what we have in here left with is actually dB is equal to mu naught I over 4 pi y, because we have another y coming from the denominator. I have y plus y, albeit we canceled one of the y squared, but we still have another one in the denominator. I have a secant squared. I know some of you are eager to cancel one of the secant squared with the cosine theta. Just leave it for right now because it's going to go on itself. Cosine theta, oh, I'm sorry, d theta, I forgot d theta in here. D theta k hat over the d, oh, the d theta is there, I'm sorry. Why did I say I removed it? It's in here. It's for part of the dx. Okay. And I'm left with 1 plus tangent squared of theta. And that is actually secant squared of theta too. So this whole thing, 1 plus tangent squared of theta, is actually secant squared of theta, which will cancel this secant squared. So that's why I didn't cancel one of the secant squared with the cosine theta, because I know it's going to go away. Okay. So the integration at the end is just cosine theta d theta from negative pi over 2 to positive pi over 2. And that is so simple that even I can do that. Okay. So B now, the sum, which is now we're going to sum, is going to be mu naught I over 4 pi y, the integral from negative pi over 2 to positive pi over 2 as cos theta d theta. And that is just the sine of theta. This is simply sine of theta. So it's sine of theta evaluated between negative pi over 2 and positive pi over 2. And this one is actually 1 minus minus 1, and this is 2 actually. So this whole integral is just 2, okay? Which cancel one of this 4 in here, and the expression for them, of course, in the k hat direction. Okay. And B in magnitude now is mu naught I over 2 pi y. Okay, this is a magnitude. So this is the magnetic field created by a wire, an infinite wire. At some point, y from it drops like 1 over y. Okay, so this is an important result. A magnetic field created by a long wire. Okay. The reason why I have to say long wire and not infinite wire is because of the fact that there is no such a thing in physics. You always have finite sizes. So what do we call an infinite wire versus an finite wire? Is how y is related to L, to the length of the wire. Okay, so the wire could really indeed have a finite length L, but L is much, much bigger than y. That's what that means. Okay, so that's what infinity means in here. The length of the wire L is very big compared to y. As a matter of fact, it doesn't have to be that big. If the wire is 1 meter long, just probably 5 centimeters away from it, 10 centimeters away from it, this expression would work beautifully for the electric field, okay? For the magnetic field, I'm sorry. So this is how to find the magnetic field for an infinite wire, okay? There is another important result that you're going to need in one of the some of the homework problems, and it was actually an exam problem last year similar to it, basically using the result from it, and that is a magnetic field created by a loop, okay? So imagine you have a loop of wire that has a current running through it, and you would want to find the magnetic field in an axis passing by its axis of symmetry, okay? So that was, like I said, in last semester, it was actually an exam for some of your classmates, the ones who, and so here is how the problem looked like. So we have a loop in here. I'm trying to draw a loop in here. Can I draw it with this tool in here? Okay, this is better. And I draw the axis of symmetry somewhere in here. Albeit now this crosses it, okay. So this is basically what I have in here. I have a current I going through this loop in this direction, okay, counterclockwise. And I want to find the magnetic field at some distance, x from the center. So this is x. And the radius in the book, they use the letter A. I really don't like the letter A in here. I'm going to use the letter R anyway. The radius of this loop. So a magnetic field of a loop of radius R and with a current I running through it, okay? So we want to find the magnetic field in here that this creates. Obviously, I'm going to take an element of the wire. So this is my DL, okay? And I want to find the magnetic field due to this element at a distance. Here is the distance really of interest. Here is my dr again. And this r is clearly from the geometry is x squared plus r squared under the square root, okay? And I'm going to sum through dl from 0 to 2 pi r to the radius of this shape in here. Ultimately, at some point, we will be interested in the case when x is equal to 0, right in the center of this loop. How much magnetic field is created by this current, okay? So that is a question that we want to know for that, okay? So think of it this way. So this is your, except I have a lot of them in here. And actually I can do this experiment in here. I can run a current through it. Do we have a battery in here somewhere? I don't see my battery in here. Here's the battery, but I don't see the battery holder. If we run a current through it, you will see that it becomes magnetized. Exactly what we're saying in here, and we can calculate the magnetic field through it, okay? So this is the shape that I have in mind. Obviously, you see it's not just one loop, it's a lot of them in here, and it's spread throughout this entire shape. So I have a lot of them in here. So what I do in this case, if I connect these two sides to a battery, which is feasible if I have a battery holder in here, and I have a lot of them somewhere, I don't have one handy. By the way, I did not receive a reply about the materials for the motor, so the motor is officially canceled, okay? Because they were supposed to provide the materials before the midterm, and I know they ordered the materials, okay? Okay, so why did I call this one dr? I'm sorry about that. This is not dr, this is actually r hat, okay? You guys need to correct me when I do mistakes, and I told you guys in the beginning of the semester that I do that a lot, so please make sure that we fix those things, okay? So we want to find the magnetic field created by this loop. Let me redraw the shape because it's kind of tilted a little bit and it looks kind of odd to you. This is not how it's supposed to be, to look like. It's supposed to be exactly sitting like this on the screen. So if I look at it from sidewise, this is how this looks like actually. It looks like this, the entire thing in here. This loop looks like this. So on one side, the current is coming out, and this is exactly what's going on in here. So the current is coming out of the screen in here, and it's going into the screen in here, and it's coming down this way. Okay, and I want to find the magnetic field at some distance, x from it. This is the direction of r hat. Okay, and this direction is r, and this is still your square. So the reason why I drew it in here is to give you the sense that this is a ring. But this is how it looks like when you look at it this way. What is my other? So this is how it looks like when you look at it this way, okay? It looks like this shape. So what you see in this case, the current is coming out and going in, but it's going through this loop this way, okay? So that is basically the illustration that I want you guys to have in your mind. So now we want to find the magnetic field, the direction of the magnetic field first. The direction of the magnetic field is perpendicular to this element. So this is just dl. This is not the entire thing. This is just an element of that. So it's going to be perpendicular to dl. Because I drew dl coming out of the screen, so the direction of the magnetic field dB has to be somewhere on the screen. On screen now. But not anywhere on the screen. First of all, it has to be here because we are trying to find it in here, okay? It also has to be perpendicular to r hat because it's a product of dl and r hat. So for that, it has to be in this direction. Obviously, it could be in this direction, but let's see which one direction makes sense. I have to have dl, which is coming out of the screen, and I have to have r hat, which is pointing down. So by the right-hand rule in here, it has to be coming out actually up this way, and it has to be perpendicular to both of them. So this is my dB. It's perpendicular to r hat, and it's perpendicular to dl by virtue of the fact that it is actually on the screen. Because anything outside of the screen, perpendicular to the screen is perpendicular to it. So this is the direction of dB. I'm going to argue by symmetry also, saying that if I take this element, it's identical to this one, the same distance. R hat is in the opposite direction. So the magnetic field is actually going to be opposite to this one. Same magnitude, same current, the same dl, the same everything. The only thing is the direction now is going to be downward. So what I'm looking at this direction. I'm looking at like a cone, okay? That's basically what this thing is. I'm looking at a cone for the entire thing, okay? So this is basically the shape I'm looking at. So by symmetry, the component in the y direction will be 0. And the z direction will be 0. So any direction other than in the x direction will cancel. So the only direction that is going to matter is the one in the x direction, that's all. And the one in the x direction is a cosine of this angle. And this angle, of course, I'm assuming this is 90 degrees perpendicular to r hat. So in this case, this angle and this angle add up to 90 degrees. And this angle and that angle add up to 90 degrees. So this angle and that angle are the same, okay? And so it's going to be dB is equal to cosine of this angle, which is the same as that angle. And that angle, the cosine of it is clearly r divided by the hypotenuse. So it's going to be dB times r divided by the hypotenuse, which is in this case square root of r squared plus x squared. So the magnetic field that is going to survive the whole operation is going to be in the x-axis by symmetry. And that is going to be equal to dB. That is going to be in the x direction only. There will be no more the y and z direction because they cancel by symmetry. As I was saying, it's a part of a cone. When you project it in all directions, give you 0. The only direction that does not cancel is the one along the x direction, along the axis of symmetry for the entire loop. So it's going to be mu naught I over 2 pi, or 4 pi, I'm sorry, 4 pi times, again, Now we have to get into the DL. So I'm going to leave the DL as is. I already resolved the direction, so there is no need now for me to write any directions. Divided by the distance squared, and the distance squared is just this hypotenuse squared, which is r squared plus x squared, times this quantity, and this is coming from the cosine of this angle. This is not 90 degrees. This whole thing is 90 degrees. This is just part of it. So this is this angle theta, if you wish, which is the same angle as theta in here. So it's going to be r divided by the square root of r squared plus x squared. Okay? So this is the entire expression for the magnetic field now. I have to sum it from 0. So DL, changes from 0 to 2 pi r. And there is nothing in here that has the angle in it whatsoever. So when I sum, all I have to do is just multiply by 2 pi r, that's all. So the whole expression now looks like this for the magnetic field, and it's all in the x direction only. It's mu naught I over 4 pi times 2 pi times r squared over the combination of this r squared plus x squared times r square root is simply r squared plus x squared, the whole thing to the power 3/2. Cancel the 2 pi with a 4 pi, and you'll be left with mu naught I over 2 times r squared over r squared plus x squared to the power 3/2. Okay, it's kind of a little bit complicated in terms of how it behaves, but in terms of overall, because of this dependency on r and x and all of that, but it's similar to the dipole. As a matter of fact, I can find the expression when x, so the dipole approximation, when x is super big compared to r, then r is neglected in here in the denominator, and we'll be finding that b is simply, you will have x squared to the power 3/2. That is x cubed. So it's mu naught I times r squared over 2x cubed. Okay, so that is in a sense basically what we have in here. Okay. An interesting result in here, and that is exactly the result that is actually was needed last time when we were doing an exam for x equals to 0, right in the center, when x is equal to 0, when we bring this whole point and put it right in here on the 0. So we just sub in here by 0, and we'll have r squared to the power 3/2, that's r cubed, and you have an r squared in here. So when you do the summation in this case inside the loop itself, is going to be mu naught I over 2r. We're going to need this result down the road, okay? We're going to need this result big time. Mu naught I divided by 2r, that's all, okay? So this is the magnetic field created by a loop inside of the loop. So if I go back to my problem, so this is exactly how much the magnetic field right inside in here, okay? Right inside the loop itself, right in the middle of the axis of symmetry, that would be that value. Obviously, I have to multiply. In this case, I have so many of them. So each one of them will create this value. Remember, mu naught is 10 to the negative 7. So even if I run a huge current in here, this r is small. This r is radius is, I don't know, it's probably the whole diameter is about 5 centimeters, okay? So this r is probably 2 centimeters in this case. So
I have a question. During the test, when or during the homework, when you ask about the current during the loop, with the loop, do we need to start from finding the angle, or we just use the last thing that we just found?
Okay, depending on the problem, Shahad, that's a good question. If the problem is already taking it in the center, you don't need to prove anything in there as long as you understand where things are coming from. That is the purpose of this exercise, is actually because sometimes you'll be given different geometries, and that is the case when you have to basically work your way through it and try to find an approximation that is different than this one's. But in this case, if you are in the center of the loop, this is what you use. If you are not in the center of the loop, you are somewhere in distance x from it, the other expression will be handy. This one will be handy. If you are far away from the loop, then in this case, you just go back as if it's a dipole approximation. By the way, in this case only, look at this expression very carefully. I'm glad you mentioned that. I times r squared. R squared is actually times the pi is the area of the loop. So pi r squared is the area of this loop. Okay, and when you multiply it by I times pi r squared is what is called the dipole moment in here, magnetic moment. So the magnetic moment in this case, mu actually, not to be confused with this constant mu naught, is the magnetic moment similar to the electrical dipole moment that we did before, okay? So in this case, the expression would look like mu naught times I pi r squared, so I introduce a pi, so it's going to be mu in the numerator divided by, I introduced the pi in the denominator, so I have better divide by it, x cubed. This looks identical to that of the electric field, with the exception of we had P in there, the dipole moment, the electrical dipole moment, and here we have the magnetic dipole moment. P in there was defined as equal to charge times distance between the two charges. And here, the magnetic moment mu is defined as area times the current, okay? That is the only difference. Everything else, there we had an electric field. Here we have a magnetic field. As a matter of fact, you can think of the magnetic field or a magnet, any magnet, even this magnet in here, as being simply a dipoles, bunch of magnetic dipoles, and each dipole has its own magnetic moment, okay? When you take physics 4D, if you're going to take physics 4D and you get into the magneton and you try to understand the magnetic field from a quantum mechanical perspective, you will be coming back to this definition of the magnetic moment, and you'll be using it extensively trying to find the magnetic properties for different atoms and different structures. So this is a very important result, okay? That if you're going to major in chemistry or you're going to do anything with chemistry, this is also an important result. This mu now is actually called the magnetic moment, not to be confused with this constant permeability of the medium, okay? I know symbols sometimes they look alike, but one of them is actually a property of your actual magnet, okay? I know we asked last time, we still have to answer the question, what is this permanent magnet different than an electromagnet? Because this is actually an electromagnet. This magnet is due to electricity. This magnetism is due to current, okay? All of these things, and even for the infinite wire, it's actually due to this one too. So all of these problems, they have to do with that, okay? So you don't have to derive these things. As a matter of fact, we're going to derive another law similar to Gauss's law, okay? That is going to be very useful so that we don't have to do this integration. If we have symmetry, then we use the so-called Ampere's law, similar to Gauss's law, where we're going to just basically calculate, instead of calculating the flux of the electric field. Remember what we did for the electrostatic part of it, we did the flux of the magnetic field, and then the flux of the magnetic field over a closed surface turned out to be the amount of charge divided by epsilon naught. In here, we're going to actually calculate the circulation of the magnetic field, and the circulation of the magnetic field, which is a line integral instead of the other one being a surface integral, the line integral will turn out to be proportional to the current enclosed, okay? And mu naught will come in handy in this case, just like epsilon naught came in handy in that expression, okay? So this is the stuff that hopefully you guys will remember when you're doing problems, okay? So you don't have to rederive things, okay? But Ampere's law, remember in your exam, you had the first problem was dealing with Gauss's law. So don't lose sight of that when we come into Ampere's law. I'm just trying to see if we covered everything we're supposed to cover in here. And as a matter of fact, Ampere's law is coming next. And before I do Ampere's law, well, let's do Ampere's law first, okay? It's still in this chapter, so I thought it's going to be next chapter. So Ampere's law, and then we're going to do interacting wires, okay? And the chapter will be covered. Ampere's law. So I'm going to take my wire, the one that I took earlier. This is an infinite wire. And at a distance, we called it Y earlier. So we're going to change the symbol in here. We're going to call it R in here, okay? Hopefully you guys don't, you're not confused with that notation. So the magnetic field, if the current is flowing this way, the magnetic field is coming from here, and in here it's going inside at the same distance R, okay? And actually it's circulating, okay? Circulating through this wire in this fashion. So the magnetic field is given by mu naught I over 2 pi times the distance, and the distance now changed from Y to R, okay? So that's the only thing different than this problem, the first problem. As a matter of fact, if I come in here and look at this entire wire, this is how it looks like. So this entire wire looks just like a dot coming to me, okay? So looks like this. The current is coming out of the screen, okay? This point will have then the magnetic field this way. At the distance R, actually, if I go to distance R, the magnetic field is the tangent to the circle whose radius is R. Everywhere. So the magnetic field B is given by that expression, and it's along the circle, along the path of the circle, whose radius is R, actually, okay? Because R does not change. If R doesn't change on the circle, then the magnitude stays the same because you're dividing by the same quantity. I is the same for the entire wire. Mu naught is constant, 2 pi is constant. So since R is the same on the circle, so the magnitude is the same, and the direction also is on that direction given by the right-hand rule. This is the right-hand rule that you need to remember now for this situation. The current is along the thumb, and the magnetic field curves per your palm, following your palm. So that is the magnetic field, how it's going, okay? So I'm going to define the circulation. It's basically this thing. The circulation as the path integral over closed path of any vector B times dl, where dl in this case is along the path, okay? So dl is along the path, and this is a vector. So any vector, the vector B now, this is its circulation. So this is by definition the circulation. Obviously it's a scalar. You can clearly see this is a dot product, not a cross product, okay? Because of the fact that I'm taking a circle, so regardless of where I start from, I'm going to go full circle. I circulate a full 360 degrees. So that's why circulation in here. And like what we were doing with the flux, when we did the flux was actually the measure of how much field lines we're leaving. Okay, this is different, okay? So if I do that, first of all, B and DL are parallel to one another in every given point because B is tangent to the surface, to the area, to the circle, I'm sorry. And since it's tangent on it, any DL I choose there is going to be parallel to it. So BDL is going to simply be BDL, okay? Because they are parallel to one another in every single point on this, the circle. Furthermore, B is constant. I was arguing earlier that it's constant because R is not changing. Since R is not changing, B will come out of the integral, and I'm left with just simply the integral of dl from 0 to 2 pi r, okay? So if I do that, this expression then will be simply equal to B times 2 pi r. And B has a 2 pi r in the denominator to begin with. And this 2 pi r will cancel that 2 pi r, and it will be left with just mu naught I. So the circulation of the magnetic field over a circle, okay, around a wire is simply mu naught times the current that runs through that wire. That's it. So it's similar to Gauss's law, except Gauss's law, you have Q over epsilon naught. But because epsilon naught was already in the denominator, it stayed in the denominator. Mu naught was already in the numerator, it stayed in the numerator. So this is similar to Gauss's law, with the exception I did not really do any other shape, because Gauss's law says that any shape, it doesn't matter, arbitrary shape, you have Q over epsilon naught. In here, this is a circle. So how about if I take a different shape? How about if I take a complicated shape? So again, I'm going to come in here, a wire. I'm looking at it coming at me with a current I. And now I'm going to take this path. Okay? At some point, I'm close from this one. So the magnetic field is still be given by mu naught I over 2 pi r. Except r now is changing. R sometimes is smaller, sometimes is bigger. So the magnetic field in this point is weaker. It's still tangent, but it's weaker than in here, which is stronger, okay? This point is actually going to be even smaller, okay? And so on and so forth, okay? Because as I move further away, I'm dividing with a bigger quantity than if I'm closer by. So how is the circulation now is going to work out for me? Well, it's going to be the same thing around this new path now. So this is closed path still, but not on a circle now. It's still a closed path, any closed path, any. Of BDL. On that integration, B is not constant and DL is not constant, but in any given point, DL and B are actually parallel to one another still. So it's still true that this product is actually equal to, on this any closed path, it's still BDL. The problem is now B and DL are not really, I'm sorry, this is not true. I have to be careful in here, I'm sorry. Okay, so yeah, B is still in this radial, in this, not radial direction, in this angular direction. So B is actually along the angle, but DL in here, you can clearly see DL and B are not actually perpendicular, are not parallel. But DL has two components still in any point. DL has a component along the angle and has a component along the radial direction. Okay. The radial direction will cancel in the dot product and you'll be left just with the angular direction. And the angular direction is actually equal to r d theta. So any vector, let me remind you from physics 4A what's going on. So if I have a vector r, I can change its length by dr and make it r plus dr. R plus dr in the r hat direction, in the radial direction only. Or I can change its direction actually, okay? And according to the direction, this one is actually r d theta, okay? In the theta direction. Theta hat direction, if you want to call it that way. This is the radial direction. So the overall change of any vector is the sum of the two. So dr actually is going to be dr in the radial direction plus r d theta in the theta hat direction. Since the vector B is always given by the right-hand rule, no matter how far we are, when we are close from it, it's this way. If you are far away from it, it's still in the circulating around it. So B itself is along the theta hat direction. DL is always going to be it can be both, okay? So when I said earlier, that's not correct. I took two specific points, but if I took any other point, that would be coming down or coming out, and that is not true that the vector DL can be in only the angular direction, the azimuthal direction. That's how it's called sometimes. So it has the both components, and this is stuff that you did in physics 4A. So now, if I do the dot product of the two, the only thing that's going to be left is this thing. So in this integration, this is the expression that we're going to be finding in here. So the integration is from theta, basically now changes from 0 to 2 pi of B, and B is still mu naught I over 2 pi r, and times this number, which is r d theta, and this r d theta is coming just from this dot product, okay? Now, obviously, the r and the r cancel, and everything else stays the same, so it's going to be mu naught I over 2 pi, and the integral from 0 to 2 pi of d theta, and that 2 is 2 pi. And the 2 pi will cancel the 2 pi, and you will end up with the same result. Okay? So regardless of whether or not you take a circle or any arbitrary path, because in any arbitrary path, as you move further away, like in here, you're changing it by an r. Okay, so this arc in here grows by that distance, but the magnetic field drops by r, and the two cancel. Okay, because your ultimate goal is to come back to your point in here. No matter which way you start from, you're going to do 2 pi. Okay, so the 2 pi will cancel the 2 pi, and at the end, the result does not matter. So in any closed path now, any, doesn't have to be a circle, any closed path, BDL is going to be equal to 0. So we did it. I'm sorry, not 0. I'm sorry, mu naught I. Okay, where I is the current enclosed by that path. So this current in here is enclosed by the path. Okay, so this result regardless now of the shape. Now the only question is, how am I going to handle more than one current? So let's say, for example, I look into this situation. I have a current I1 coming out and a current I2 coming out and a current I3 going in, okay? And I want to find the circulation of these 3 currents along this path, okay? Well, in this situation, do you guys remember who should we call? Our BFF? This is the same thing that we use in electrostatics.
The superposition
Did
principle.
somebody type? Thank you very much. Thank you much. Yep, that's it. We're going to invoke the superposition. Superposition. So basically what we do in this case is we're going to take the circulation along this path for I1, which is going to give me basically the circulation due to just this one, which is going to be B1 DL is going to be mu naught I 1, and the same thing for the B2 DL along the same path. So the DL is not changing, okay? It's mu naught I2. And then the sign situation now, we have to be very careful in here, okay? I'm going to assume that this one is positive. This one is positive, this one is negative. So anytime, because we're going through the circulation in this direction, in counterclockwise direction, okay? Any current that is coming out and you're going counterclockwise is positive. Any current, since you're going still counterclockwise and the current is going into the screen, that is a negative current, that's all. So I3 now needs to be treated as a negative current. So the circulation coming from I3 is going to be a negative value, that's all, okay? So the circulation B3 DL is going to be mu naught I3, assuming that I3 is negative. Okay? Because we're going counterclockwise, which is a positive direction, always circulate around. And then any current we trap it, finding it coming out, that is positive. Any current that is going in, that is negative. Okay? So this is the convention in here for this size in here. Obviously, the integral is a linear operation. So the circulation of B1 plus B2 plus B3, which is by superposition B, the entire magnetic field, this one, all of them, BDL, is simply equal to mu naught, the sum, the algebraic sum, meaning that some are positive and some are negative of these currents, okay? Enclosed currents. Remember, these wires are huge, okay? And we're looking at them from just from the one angle, okay? So this is basically how we have it here. There is only one minor thing that we need to make sure, and the reason why I've been calling it enclosed. What happens about when the current is not enclosed? Well, we can do it this way. Actually, you can do it. So if we have a current coming out of the screen and I want to find the circulation of B in this sense in here, so it doesn't matter. So if I start calculating in here, let's say this is the starting point. My starting point is this angle. This is a wire, okay? So my starting point is this angle. So this angle probably is going to change to this value and then starts to decrease a little. Then, so it's theta naught, okay? Then it's going to come in here. Then it's going to increase from this value all the way to this value. And now it has increased dramatically to this value. Now it's going to decrease back. It's going to become smaller and smaller back to the starting point. So the integral is going to be from theta naught to theta naught of BDL. And that is equal to 0 because the boundaries of integration are the same. So that's why I've been saying enclosed, because if the current is not enclosed by the path, the contribution is null. Okay, this is identical to Gauss's law. So Ampere's law says the following. The circulation, and remember, the circulation has a different definition than the flux. Okay, the flux has an electric field times a vector times an area in general. The circulation is actually a vector times the length. Okay, the circulation of a magnetic field over a closed path is mu naught, or permeability in this case, times the algebraic sum of the currents enclosed by the path. The currents enclosed by the path. So this is basically what Ampere's law is. Okay. It is a matter of exercise that we're going to do at the end using Stokes' theorem. The circulation will be converted into a surface integral, and we're going to find the current density like we defined it in the current, and we're going to find an expression that going to involve the curl of a vector with its current density. So basically, this is in a nutshell. No, we still have one item in here. I'm looking at the summary in here and stuff of the book because I don't want to miss anything in here from this chapter, because we still have chapter 29 coming. Okay, what if I have two wires next to one another? Both of them have currents running in the same direction now. Experience shows that one of them will repel the other. So let's see in here what's going on between two wires. So this current has this wire has a current I1, this one has a current I2, and the separation between the two wires is actually a distance d. So we want to find the force exerted by wire 1 on wire 2 in here. So I want to find this force in here. So what do I do in this case? I want to find the magnetic field in that point. Since the current is coming, it's going up, okay? Then if I do my right-hand rule, the magnetic field produced by I1 will be here, coming out of the screen, actually. Okay? So it's going to be coming out of the screen. It's going to go in from this side, but come out of the other side. Okay? So that is the magnetic field. And the magnetic field simply will be equal to mu naught I1 over 2 pi times the distance d. Okay, this distance between them. Now this wire from the previous chapter would be, since now it's sitting inside a magnetic field and it has a current I moving upward. So if I take a length L of it, it's going to be subject to a force which is equal to its current, which is I2, times L times so this is the force on 2, by the way, okay, due to 1. So this is F2. First of all, it's perpendicular to both of them. So the current is going up, the force is, I'm sorry, did I say repel? They attract, okay? The force, the current is going up, the magnetic field is coming out, so now the direction of the force is actually going to be pointing this way. So this is F21. So it's going to be attracted to the other wire. So this is something different than what you have seen. Opposite charges in electricity, they repel. They attract. Similar charges in electrostatics, they repel. Similar currents in here, they attract, actually. Okay, so this is kind of something that you have to remember. So in here, the current in here, and the same thing for the other wire, apparently it should go from this way to here. So let's find this force in here, okay? So times the magnetic field in that point. And the magnetic field is due to 1, by the way. So this magnetic field is due to wire 1. So if I sub the values in here, so F on 2,1 is equal to I2 times L times mu naught times I1 divided by 2 pi times the distance between them. And by definition, I'm going to define the force per unit length, F2. So this is by definition is F21 by unit length, okay? Because of course, if I take a mile long wire, subject to a magnetic field is going to be subject to a lot of force versus if I take just a centimeter of it. So that's why we really work with this force, which is units of Newton per meter, okay? So this force now, if we sub everything in here correctly, it's mu naught I1, I2 divided by 2 pi times the distance between them. Now, the same calculation could be argued for the other one by third law of Newton, if you like. This F12 will have the same identical value. So the force per unit length on the first wire due to the second one is going to be mu naught I2, I1 over 2 pi times the distance between them. Now, if the two currents are in opposite direction, if this one is going up and the other one is coming down, that is going to be a repulsion. Okay, so if this is still going up and this current is coming down, everything calculation is going to be the same, except now as current is coming down and the magnetic field is coming out. So the force now is going to be pointing in the opposite direction, pushing it away from it. So currents in the same direction, attract. Opposite direction, repel. This is kind of backward than what we have seen in the case of electrostatics. The entire chapter we covered it. That's good. I mean, I was not sure we could do it. And I'm hoping that you guys go through all of these concepts and try to understand them. And Shahad has a very good question that hopefully everybody also will pick up on it. Give me the bottom line. I don't care about all of this theory. What am I going to use? And that is a legitimate question. I want to be just an engineer. I have other things to take care of. I'm not going to major in physics. These are important. These two results are important. Ampere's law is extremely important. So exam time, I want to hold you to it again, okay? So I want you to understand how to calculate this circulation in here, this example. So if I took a surface, for example, I mean, not the surface, if I take this path and I tell you through the path 1, obviously, I'm not sharing the screen, sorry. So if I take this path, for example, path 2, and I tell you to find the circulation of the magnetic field around path 2, so obviously it's going to just be mu naught times I2, okay? If I tell you this path, for example, we want to find it, it's going to be mu naught times I1 minus I3, okay? So that is something that you need to be held responsible for, okay? So the other question that I want you to remind you of, this result I used extensively for an infinite wire, okay? It's mu naught I divided by 2 pi d or 2 pi r or 2 pi y. So that result that we started with is a very important. That gives me the magnetic field any point away from an infinite long wire. As I said before, this question came in an exam last semester for this loop, okay? Because loops are extremely important. They help us understand actually this connection between the dipole, electrical dipole, and actually the magnetic dipole, okay? And unfortunately, like I said, the project for the motor has been canceled because of the low response. No response whatsoever at this point from the basically the people who order materials. This would have been important because then you will make your own loop, and the loop will have a current in it, and you're going to estimate how much torque is going to be created, and that is going to, you need to calculate your magnetic moment, and you do the calculation in that for that project. Unfortunately, like I said, we're going nowhere with that. We still have about a minute. I'm going to see you guys on Wednesday, where we're going to do problems from this chapter, and that is where the question of Shahad will take actually far more shape, because you will see what is important from these things in terms of calculations. And we're going to do examples from this chapter. We still have chapter 29 and 30. Oh man, what we're going to do a lot of, we're going to introduce the induction. We're going to get into the AC currents, and we're going to get more circuits before we get into chapter 32, which is the EM waves, electromagnetic waves. So we still have quite a few stuff to cover. Good. Yes.
Sounds good.
Okay. I'll see you guys. Thank you. I'll see you guys Wednesday. Okay.
See you
Bye.
Wednesday.